Okay.
Yeah.
Hi, my name is Mahati Chamarthi. I work for Intel as a software engineer. Today we're going to talk about Ceph RBD performance in a hyper-converged environment.
And I'm Michael Cadera, and I'm here, actually I'm covering for Tushar, who unfortunately was called away on other business. And so what I'll do is I'll be talking about the hyper-converged environment and a little bit about myself. I started in Intel in our data center group, and I spent a lot more time in IT, actually working with OpenStack. I've been working on OpenStack since the Diablo days. Well, that's where we deployed our first hybrid cloud solution. I worked on platform as a service as well. Now today, I'm in Intel's Open Source Technology Center. And what I do is I work with customers to help them enable Intel technology. So as teams like Mahati's work on new features within Ceph or OpenStack or Kubernetes, I'll work with the customers to deploy those new types of solutions in their environment and hopefully tune them for the best workloads and hopefully take advantage of as many of Intel technologies. Now, today as we go through this, as I mentioned, we will be talking about hyper-converged environments. And as we go through this, we're going to give you a little bit more of the guidance for how you can tune or actually analyze your environment. Now, a little bit about hyper-converged environments. If you think about the traditional three-tier architecture that the cloud was really formed on with compute, storage, and networking, it works great. But now if you look at the technology that's available today with advancements in CPU, memory, and SSDs, they can now be combined into one, all the services can be combined into one system, allowing you to get more out of a standard commodity off-the-shelf solution. So benefits that this offers is allowing you to scale in smaller increments as well, and reducing the number of SKUs, so you don't have to have specialists on site to tune that environment, a specific networking or storage solution, as well as you can just manage your environment using the cloud solutions we have today, like OpenStack. Now, equally with the benefits you gain with hyperconverged, there's trade-offs you always make in tuning them. So for example, if you need to care about specific quality of service with some very dependent applications, and if you start having degradation in some of those services, it can just make your environment spiral out of control, which I'm sure we've seen with other things. So that's what we wanted to do, is talk about that today. We're going to talk about some of the general use cases that can be used for not only enterprise, but telco and NFV as well. So looking at the overall hyper-converged infrastructure market, there's been significant growth in its implementation over the last few years. And so if you look at just the trend going forward, we've had 64% increase just year over year in the growth of those systems being implemented. Additionally, cloud is, as we all know, growing fast. So we're almost at a 7% faster growth rate in hyperconverged versus that traditional three-tier architecture. Now, what the majority of enterprises are doing today and why they're going after the hyper-converged infrastructure is what I initially talked about, the infrastructure cost, but there's definitely more to it than that. I mean, really looking at the benefit of controlling the IT sprawl with different types of platforms involved, being able to look at it from a performance perspective, because now you can look at those latency-sensitive applications and co-host them where the data is, or some of those bottlenecks that may have been in the distributed systems had been impacting those applications. And management challenges, as I mentioned, you don't have to have a specialist involved, but overall you can see that many of the organizations are using hyperconverged. I'm sure that there are many here that are doing it. And if they're not, you can see that those that aren't the 26% are looking at doing that going forward. So looking quickly at how they're using it, if you look at the smaller companies that are implementing it, there's some that are still moving to just cloud use cases in general, moving from physical to virtualized. But if you look at all of them from the small to medium size, they're all using hyperconverged in both private and public and hybrid solutions. Now, from an enterprise perspective, what you see on the screen is exactly the type of workloads you'd see in the enterprise, with database taking a large use case there, and then cloud hosting. And one of the things that I thought was interesting is business intelligence. They're all, for the other ones, they're very equal. But I read an article last night from TBR as well, and it was kind of interesting that with all the growth of Internet of Things and the amount of data that we're storing these days, is that business intelligence and analytics on Hyperconverged is actually the fastest growing. And so that was over 30% in comparison with others. But it's not just enterprise use cases. So Tushar had presented with AT&T earlier this week on Monday, and they had talked about high performance Ceph for Hyper-converged Telco NFV solutions. And so they go in depth into their solution there with their integrated cloud and their network cloud. And so, as I mentioned, we'll focus more on the tools that are available and some of the knobs you can turn to help you better get the better performance out of the environment. But I encourage you, when the session is posted, to go ahead and take a look at that. Okay, so let's start looking at some of the knobs that you can turn within the environment and how it has an impact. So first, what we'll look at is how we're going to balance things out with some of the very common approaches that you'd expect first, by setting quotas on IOPS for the tenant VMs, and then we'll look at CPU constraining or putting a budget on the Ceph process and how that impacts the overall performance. So a little bit about the test environment. This was a 10-node infrastructure using Intel Xeon, the latest platforms that you'd expect, 348 gigs of RAM, and we had 4 terabit SSDs, and then we had 2 of the dual interface NICs, so we had them bound at 100 gigs, so they're all linked there. So OpenStack, Newton, and the Ceph versions you can see as well. So enough of the setup, let's look at some data. So by constraining the overall IOPS and setting that quota on the tenant, and remember this is a 10-node environment, so you're seeing that the scalability is really predictable. When it started getting up to the 45 nodes or VMs per node, that's when you started seeing that significant drop in IOPS. And looking at it a little bit further, it wasn't just a little bit, it was a significant drop. Every single VM really caused that spiral out of control. But you can see one thing that's very interesting is that a very predictable, it's when you start getting up to that over-provisioning and really putting that pressure in for contention of resources in your environment, how it can impact your overall resources and demand on them. Now let's look at the CPU consumption. So we first started looking at 15 to 20% because that is a very common benchmark to go after for hyper-converged infrastructure for storage services. And so what you're looking at here, this graph, is to share just some basic information about how we constrain them. As you can see, the green bar is at 20%, and then as reads increase, you're seeing libvirt actually starting to consume those resources. But going a little bit further into it, this is where we're starting to scale with 400 total virtual machines with a queue depth of 8, and so the 4K page read and write, so it's a little smaller pages. And looking at the overall performance, what you really start to see here is that by cutting the CPU quota in half, that really was not an impact on the environment. It's really when you started getting below 50% that you started to see that impact. And so that sweet spot is between 25% and 55% or 50% constrained. But when you got below what many people thought was a standard for software-defined infrastructure on hyper-converged, you saw that significant impact of 30% on the IOPS. But with hyper-converged, it's not just looking at the services that you would have in a traditional 3-tier environment, like, for example, Ceph on its own standalone box. You have to look at the impact of the Ceph client as well. Now, looking at it, the Ceph client it actually performs really well the more cores you start adding to it. But you see that there is a point that adding more cores just doesn't make it go faster. So adding a little bit more to this as you dig into on the left-hand side, that is looking at the overall the cluster and then digging into a single node. What you're really seeing is that as we started getting up to those 32 cores, that's where that benefit really didn't, adding more cores didn't give you that benefit. But really the takeaway, if you really look at what we just saw with the servers, the object storage daemons, and the client, is that they can really play well together, is that the client is not going to be a resource hog, so it gives you an opportunity to take advantage of the resources for and tuning those and dedicating those resources to the Ceph services. Okay, well, let me hand it over to you, or you can go into additional tools.
Yeah.
Okay.
Thank you, Michael, for the introduction. So a quick introduction to what RBD is and what RBD images are and their features. RBD images are they're striped over objects, and then they're stored over the distributed object store, RADOS. And the read and write requests for the image are distributed across many nodes in the cluster. So it prevents any single node from becoming a bottleneck when an individual image gets large or busy. So as you can see in the figure, it interacts with the RADOS either via kernel module, that is KRBD, or the user space library, that is librd. Kernel module leverages the page cache, and the librd has its own user space in-memory cache. And RBD layering refers to copy on write, which allows for faster image creation, and its snapshots are generally read-only, so it will prevent any accidental writing on the images when snapshots are taken. It has a vast integration with QEMU, libvirt, and Linux kernel. And then RBD mirroring is where you have a bunch of images. If you want, you can actually either keep it for a single pool or a set of specific images. And you can configure it using the RBD daemon. Sorry. Anyway, so no, I can't scroll this down.
Well, this needs to scroll down.
It's okay. Sorry for that. So when an RBD image is created and when you want to look at how that is stored, these are the fragments within the pool that are stored. RBD data is the raw image. ID is that's locatable using name and also vice versa. Header has usually image metadata, and object map is used to locate where actually objects are stored on the disk. Directory has generally a list of images within a pool. In this case, there's only one image which we're looking at as a librd test. So the data is also related to only single image. And when you run an info command on an image called as test, it lists out a bunch of default features, wherein, for instance, like layering, which enables to clone. Exclusive lock requires you to get a lock on an object before you write to it. And object map is something which helps you track where are the objects actually located on disk. And deep flatten is something where a child image is separated from the parent image, and then parent image becomes deletable, but the child image still retains a snapshot history. And fastdiff will generate a differences between a snapshot image and actual data usage of the snapshot. So now, with introduction out of the way and what images are, this is a general request flow from librd to the OSD and back from OSD until it finishes the request. So the request goes through initially through librd, where it calculates tribe counts, tribe units, and how many number of object requests are needed. And once it goes to librados, it creates an op data structure which holds data like object ID, object location, and offset, and length of the object, and also if there are any callbacks, those are loaded into onComplete. It prepares the operation and it sends to the objector module. And in objector module, if there is any recalculation of an OSD map, those kind of operations happen, which then sends prepares the OSD operation and includes some of the settings like priority or what message type does need to be included with. These are all the details that are packaged and that are sent across to the messenger. And messenger sends it to the OSD, and OSD processes it, and it's back to the messenger and to the objector. And here's where, if there are any callbacks, for instance, it could be a complete callback where the memory is written only, the data is written only on the memory of all replicas, or it could be safe, where it's actually on the disk for all the replicas. Here's where a context switch happens, which perhaps could be an overhead. Having a context switch at that level, because having a context switch and then queuing all the requests and processing them could perhaps be improved. We'll get to that a little later. So the AIO completion, and that completes the request. There has been a lot of discussion in the Ceph community about what tracing tools, or what is efficient or what is not, and at what level of data do we get with the existing tools. So I'd like to just briefly discuss about what tools do we have as of today, and what are these, and what kind of analysis do they give, and we'll also look at a bunch of them in detail. Clearly, first one is using the Ceph subsystem logging, and which you can enable in the ceph.conf. And Wireshark and Tshark are used for network traffic analysis. Zipkin is an end-to-end visualization tracing tool, which has recently been integrated during an internship, as an internship project. And Ceph perf counters are Ceph internal infrastructure metrics, which can be established on the librd side by using RBD replay. And then there's perf tool and flame charts, which will give you how the CPU is doing. And then event trace is essentially an LTTNG, like LTTNG trace points, except it makes it easier for you to have it in code. There's also a bit of detail about that later in the slides. And one of the ongoing discussions for future considerations has been about open tracing. So it's and its integration into Ceph. So we did a bit of an analysis with using Zipkin tool with an environment like this. It has 6 OSDs attached to one single NVMe. The CPU was Xeon CPU, and it had Linux Ubuntu. It has one monitor, a single manager, and BlueStore as a backend. The traces are collected using LTTNG, and they are sent using FIO, or not just FIO. Using FIO, we collected LTTNG traces, and those were sent to Zipkin. Here's a brief description of how the Zipkin is set up. It's not exhaustive, so there's a link at the bottom. That's not really up to date, but it would still help you a little bit with the setup. So essentially, the things to do within Ceph code is build the code with block-in option, and have the block-in trace all option, and enable that in ceph.conf. Enable the Zipkin LTTNG events, and when you start an LTTNG tracing, and use Babel trace Zipkin to send traces to Zipkin website. That is, you actually have to download zipkin.jar and run it using a Java command. So these kind of details are the ones that are not on the slide, a little bit missed out, are covered in the link below. So this is how it looks like when you send a trace to Zipkin. The visualization looks like this. The highlighted part, you can actually sort it either with the shortest time or the longest time. And it shows for a request, for an IO request, how many services are used, how many times have they been touched upon. For instance, on the highlighted one, messenger has been used for five times and objective for 3 times, and it has to use OSD1 and OSD4 to write data. Going a little bit into the details, this is a stack trace of the critical path of librd, and you can see it displays the latency at the top, and it tells you how many services are used, at what depth is it collecting data, and how many microseconds it takes to do an operation. So getting a little more into detail, and when I click on an objector, and I click on objector because that's pretty much the last part on the client side where the request actually leaves and goes to the OSD. So when it leaves the objector, that's when the async writing message on the screen. So that's when it actually leaves the client side. And then once it processes the request on the OSD side and it's back to the client, it calls on the decoded trace. So when you subtract those two values, you would get an estimate of how much time it actually took to process a request, a single request. So using those values, this is a representation of the amount of time that it took on the client side for each module. As you can see, the messenger takes a good chunk of time, and then the next one is network processing, and then the objector consumes. A similar data was taken for read, and as it is supposed to be for read, it's a little lesser, but the distribution of time is still quite similar. Messenger does take quite a bit of time. So we've been working on trying to get these numbers down, and we've been trying to look at the code and see what areas could perhaps be tweaked around and improved. So one of a few of them are perhaps using, currently AIO callbacks actually do a context switch, and they go to a finisher queue. So in order to avoid that, perhaps use polling, or maybe leverage the fast dispatch messaging, which already exists in Ceph code. And the other one is there isn't memory management on the messenger side isn't as effective. Perhaps that could be cleaned up a little bit, and then you could get back and do some elimination of memory copying on the C API. And one other area is possibly some of the journal IO improvements, which is perhaps sending some parallel updates. So these are some of the ideas that we thought, and these are all actually somewhere on the Trello as well, and we're actively looking at a few of them, and we think that they could significantly improve the latency times. So we can take a look at a bunch of other tools that we had used that helped us gather data at a granular level. Perf counters, so these are Ceph internal infrastructure metrics, and usually you could use a socket daemon and retrieve these for OSD or services like that. But for the librd, I had to go and replay the workloads, that is using RBD replay prep. It's an existing command line tool, and when you send across the LTTNG traces, and then you can replay them using the option dump perf counters. It gathers, it gives out information like that. It displays what the metrics for messenger and for each library, and how much it took for Redis client. You could also give some custom metrics within the code, and the sum that's being displayed is in the average count is the number of operations, and the sum is the actually number of seconds, and average count is the number of operations that it took. So if you do a division of them, you get the average time. This data was collected on a write request. So there's nothing displayed for read or other operations. And this is just to give an idea, because a lot of people within the community had discussed that there aren't enough tools, or there isn't enough tools to get level at a granular level data. But this is quite helpful, and this could also be perhaps customized, although it will take a little bit extra code and a bit of a knowledge of how this needs to be implemented. The other one is event trace. This is LTTNG based. Essentially what it does is helps you insert an LTTNG trace really easily. If you have to usually go and get an LTTNG trace in a code like Ceph, in a code base like Ceph, then you will have to, for each of them, you'll have to create a separate module. So instead of that, event trace itself is a module that will enable you to gather traces by inserting just one line of code, but it still will generate a lot of data. So you would need other algorithms to get that data into some form of readable format. So in order to use that, you include a header and a line of code functrace and pass a Ceph context value. So these are a couple of workloads that were taken on a single OSD node using event trace, and these were the config caches disabled on a single IO depth. This was just to analyze how it works on how the client-side performance looks like with one request IO depth and on a single OSD node. So this data was collected using a bunch of algorithms to make it look like this, and these are also available on GitHub. This is the sequence of operations that happens on the client side. This is not exhaustive, but this represents a crucial portion of the data path. And it shows how librd library maps data blocks into objects and then stores them into clusters and stripes as data objects and replicates them. So this process is listed out here. The write pre is what happens before it's mostly like a preparation of a request before it's actually sent to the disk. And the write flat is where the actual write happens and data actually goes and sits on the disk. So a write flat itself takes a good amount of time, but even before that, converting into extents and calculating number of object requests also takes quite, like you can see, these numbers are microseconds. So it takes about 169 seconds to take the request in and convert them into other object requests. And then to actually send the request is where it takes 139 microseconds. Similar data was collected for random read, and it's a similar config. Cache is also disabled on this. So this lists out the process of how what happens when a read request is sent. So there is no action of actually writing to the disk. So what you're seeing is only the amount of processing that it requires to actually send the request for a read, and it takes quite nearly half the time as it would for a write request. And gathering all of this data, and these are only a couple of sample workloads that we're talking about today, but putting them all together and visualizing and actually getting an idea of how the time is distributed on the client side, we try to represent that. So a lot of processing happens on the library side, as you can see, and then the next good chunk of time is taken in Objector and not librados. And there's a good scope of improvements on library side, and I'm aware that there is caching work also going on, so that will also help in reducing the latency times. That's about it. What we have. Would you like to summarize?
Sure, and bringing this all together, really there's a lot of tools available to leverage in benchmarking and getting the best performance out of your hyper-converged infrastructure. And so really pay attention to those bottlenecks that they expose and look for those areas of optimization. And within the tools that we've gone through today, there's a lot of them all available within the Ceph community. And so we encourage you to go and get involved with them and be a participant within the IRC channels as well as on GitHub as well. All right, thank you.
Thank you. Okay, looks like no questions. Oh, sorry.
It's a long walk.
Yes, it is.
Did you do your data collection from with IOs generated inside of VM, or did you just use librd to do that?
Right, directly librd. For all the data that was shown in this presentation, it's all using librd, not virtual machine.
Have you done any of that data collection through the VM to QEMU and out to Ceph?
We've done some, but not as extensively. Yeah, we don't have extensive data as of today using QEMU or other tools like that, yeah.
And have you fixed any of the problems you've seen yet?
So the first one that I mentioned is something that's work in progress, you could say. Yeah, the rest of the stuff are still just out there, but the first one in the IO optimizations that is trying to get the AIO callbacks to use some other methodology, that's in discussion, and perhaps and the one I'm trying to work on it. Yeah.
Cool, thanks.
Yeah.
You had 6 OSDs on one NVMe.
Mm-hmm.
Isn't that a little unusual? I've heard of 2, but is 6 something that's a production recommendation?
That wasn't a production environment. That was exclusively created to test. It's really a test environment. It's mostly like keep on adding OSDs until you get a flat out performance. So I had tried with 6 and 9. So 6 was it. So yeah. Okay.
All right, thank you very much.